Alright, so this is section 7.3, which is on the eigenvalue method for linear systems. So we're going to discuss a very special case for linear systems. So x prime equals to a times x of t times. So in this case, A is a matrix with all constant entries. So there's no e to the t in the entry, there's no 2t or t squared in the entries. The entries are all numbers. Okay, and we're gonna just do a special case that A is diagonalizable. So let's recall from chapter 6, if matrix A is diagonalizable means that A is equal to BDP inverse, and D is the diagonal matrix with diagonals being all the eigenvalues, and P is the matrix with the columns being the eigenvectors. Okay, so lambda I are eigenvalues, and Vi are eigenvectors. Okay, so let's see how we can solve this. So let's rewrite the equation. Let's drop the t. So x prime equals to a times x, and a is PDP inverse. So that means x prime is PDP inverse times x. And let's multiply both sides by P inverse on the left. So we get P inverse on both sides on the left. P inverse times P is the identity matrix, which canceled, so this cancel. So we get P inverse x prime equals to D times P inverse x. Okay, and let's move this down a little bit. So because P is constant, P inverse times P inverse is also constant, so P inverse x prime is the same as P inverse times x, the whole thing, the derivative, equals to D times P inverse x. Okay, so let's call P inverse x a different name. Let's call it y. So this is y, this is also y. So the new equation we get is y prime equal to D times y. But this is a much easier equation because D is a diagonal matrix. So if you suppose y is equal to y1, y2, all the way to yn, and when we recall D is lambda 1, lambda 2, lambda n on the diagonals, and then everything else is 0, then we get the equation is telling us that y1 prime, y2 prime, yn prime is equal to lambda 1, lambda 2, lambda n times y1, y2, yn. Do the matrix multiplication together, we get this is n vector lambda 1, y1, lambda 2, y2, all the way to lambda n, yn. So what we got is the system of independent equations. So this is telling you that y1 prime is lambda 1 times y1, y2 prime is lambda 2 times y2, and all the way yn prime is lambda n times yn. We know how to solve this. This was introduced in Calc 2. A derivative function is proportional to the function itself. All these are exponential functions. So this tells you that y1 is e to the lambda 1 times t multiplied by an unknown constant, and y2 is c2 times e to the lambda 2t, and yn is cn times e to the lambda nt. So y, the vector, is equal to c1 e to the lambda 1t, c2 lambda e to the lambda 2t, and cn e to the lambda nt. Okay. So solving for y is really easy because the function, the coefficients, the diagonal matrix. Now we have y equal to this number. Recall from above that P of x, P inverse x is equal to y. So P inverse x equal to y. Let's keep the space here. If you multiply by P on both sides, on the left again, these two cancel again. So we get x is P times y. Okay, and let's recall P is the matrix with columns being the eigenvectors. And y is right above here. So y is the vector with c1 e to the lambda 1t, c2 e to the lambda 2t, all the way to cn e to the lambda nt. All right. Now, when you multiply these two things together, you notice that c1 times e to the lambda 1t is multiplied with every single entry on v1, and c2 times e to the lambda 2t is multiplied with every single entry on v2, and cn e to the lambda nt is multiplied with every single entry on vn. So this can be rewritten as c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2 plus all the way to cn e to the lambda nt times vn. Alright, so this is our theorem. The general solution is of the form x t is equal to c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2 plus all the way plus cn e to the lambda nt lambda nt times vn. So this is very important. This is the general solution for linear systems with constant coefficients. I'm going to be using this for the whole throughout the whole section.